Welcome to section 7.4 on marginal distributions and independence. The goal of this section is to define the marginal distributions of a random variable in terms of a joint distribution, and to use marginal distributions to define the independence of two random variables. 7.4.1 Marginal distributions. So before we look at marginal distributions, let's just revisit a few concepts from your first probability course. Definition 7.4.1. Two events or sets A and B are called mutually exclusive or disjoint if the intersection of them is empty. If A intersect B gives you the empty set. In a Venn diagram, mutually exclusive sets can be represented as the follows. So if we have S as the entire space, then mutually exclusive sets A and B have no overlap. They do not intersect. Two events or sets A or B are called exhaustive if A union B is equal to S, where S is the entire sample space. In a Venn diagram, exhaustive sets can be represented as follows. So you can take a set A, which might look something like this, and a set B, which might look something like this. They can overlap, and that's not a good drawing because I have a little gap down here, and that is not at all what I want. So let's get B looking a little bit better there. Okay, so now we've got a set B, we've got a set A. They take up the entire space, and they may or may not have some overlap. The ones that I have here do. Events or sets A1 through AN are called a partition of the sample space if both of these things are true. If they are both exhaustive and pairwise mutually exclusive. So if we want to demonstrate that in a Venn diagram, then we need both of these images to be true at the same time. We need to fill up all of S at the same time having no overlap between the sets. So we can have something like this if we have set A1, which is here, and then A2, which has no overlap, and A3, A4, etc., going down to finish and fill up all of the space N, right? So there's no gap here. You're imagining sets completely filling up that sample space. So a partition is exhaustive, fills up all of S, and mutually exclusive. There is no overlap between any of these events or sets. Theorem 7.4.1 is the law of total probability, and it is exactly about partitions and another event. So let A1 through AN be a partition of the sample space, and let X be any other event. Then the probability of X is the probability of X intersect A1 plus the probability of X intersect A2 all the way up to the probability of X intersect AN. And if we want to represent this in a Venn diagram, well, we can take our partition from before and put it here and add in another set X on top of it. So if we've got this event X here, that's our X. And the law of probability, of total probability, is saying, well, to get the total probability here, you can just add up the little pieces because they don't overlap. So the probability of X intersect A1 is there, and the probability of X intersect A2 is there, and A3 is there, and so on and so forth. And you end up by adding together all these disjoint little pieces, you end up by filling up the entire space S, right? So we're imagining that there's sets there as well, so that you're getting the entire probability of X by intersecting with each of the elements of the partition. In the next video, we'll go and define marginal distributions, and then we'll see an example where we use the law of total probability and relate it to a marginal probability mass function.